Well, hi, good morning. Thanks so much for coming and joining me here in my shop on February 13th. And if you're one of my viewers who clicks the like button, I just want to thank you very much for doing that. The likes are very encouraging for me and kind of keep me going in doing these videos. So thank you very much for that. Now, what am I going to do with this radio? So I think it's capacitor time. There's quite a few capacitors underneath, old capacitors that are almost certainly in need of replacement. We don't know that for absolutely sure. But you'd have to guess all these paper wax ones are in bad shape and dragging down the performance of the radio. So I think I want to start changing them out, and I want to start with the audio capacitors. And you know what? I think it means I'm going to have to take a look at the schematic and kind of just see what we've got available in terms of information for this radio. I haven't even downloaded the schematic yet. Yeah, that's really the starting point, isn't it? Okay, let me get the schematic. Okay, there's a fantastic schematic here and information that has made me rethink my approach this morning. Maybe I won't focus so much on the audio side of things, but rather on a couple of safety issues with this radio. Because I know the owner is using the Phono jack on the back, and I think, you know, if everything's good and correct, then there's really not much problem there in doing that. But I think it would help if the owner of this radio understood a little more about what's going on with it, and me too. I need to understand a little more about it. Okay, now let's just take a look at this schematic. So here's the schematic. Here's some sort of overview information, and then here's some detailed information mostly around how to do the alignment. So let's start with this page here. Let's just take a look at what this page offers. So we have the dial cord information. The dial cord on this radio is in great shape, so I don't think there's any need to study this at all. Down here we have the layout diagram. 150 volt, 8 watt light bulb. So the owner told me he got the light bulb that's in there, and I think it's a little less than 8 watts, but I'm sure it's bright enough to do the job, so that's good. Here we can see there's that funny piece I was talking about yesterday. That's helping to isolate the capacitor frame from the chassis. Let's see here. I think, maybe the reason for isolating the frame from the chassis is because the chassis, as we know now, we'll see on the schematic, is not integrally involved in the operation of the radio. Some of these radios, the chassis is busy playing the role of the B- ground point, if you like, and that's a very different thing from what's going on in this radio. So in the earlier example I just gave, where the chassis is actually the B- point, and this capacitor frame would probably be bolted solid to the chassis. But here, in this case, since the chassis is actually an isolated chunk of metal, just happens to be very closely associated to the radio inside it, the frame cannot be bolted directly to the chassis, or that would short the chassis into the radio circuit. I'm going to guess the frame here is running with a minus, is connected to the minus B, or B- rather. Not sure of that, but I think that's what's going on there. Here's all these adjustment screws all laid out nicely, what they do and how to use them, basically, what frequency to have the radio on when you adjust them. That's great. Tube layout. Capacitor here, main capacitor is a 3-parter because they show 3 numbers. And you can see the 2 IF transformers, as we saw yesterday. Screw in the top, and it says L14 underneath. That's what I noticed. You have to get up underneath with a screwdriver. Insert it way inside this can to get to the screw, which is unusual, a little bit unusual. In most cases, when you have and I assume the screw here is a capacitor, but I guess we'll see that on the schematic. This would not be, there'd be 2 of them on the top. let's take a look right away. Is this a capacitor? Well, it isn't. Well, we don't know. Well, we do. L14. It's not mentioning a capacitor, so I have a feeling this is actually a slug. Looks like a metal slug. That's what it looks like when you look down at it. So, okay, no capacitor involved. All slugs. That all makes sense. Got my head clear a little bit. I mean, that is the reason why I'm looking at the schematic here and information, is to get the right ideas in my head and get the wrong ones out as best I can, anyway. So we'll just take a glance at this right now, how to remove the chassis. It does mention about remove the pointer from the front of the cabinet by sliding it to the right. Hold pointer slider from inside the cabinet if necessary. So we already saw that the pointer is arranged so it can be disconnected or just popped off in order to get the chassis out. Here's the equipment required. I already looked at this and I noticed this one, line isolating transformer. So preferred but not essential. Well, what is preferred? This whole thing is preferred? 1-to-1 ratio transformer. That must be what they're talking about, the whole thing. So you don't need it necessarily, but a line isolating transformer makes this a little safer to do, a little less complicated in a way, and that's what I'm using. I have a line isolation transformer that's powering the radio. So we won't go through this alignment procedure yet, but we'll look at these notes just to see if they have something hidden here. Unscrew oscillator trimmers approximately 3 turns from tight. Then turn adjustment clockwise until first output peak is obtained. So a lot of these coils have 2 peaks, and you can easily align something on the wrong peak. So this is a typical way to get you to the right peak. There's other ways they instruct you to get to the correct peak. This is how they are instructing it. Rock the tuning capacitor slowly back and forth while adjusting the antenna trimmer. Okay, range, audio output, 1 watt undistorted. Current drain, so the radio should be drawing about 1/3 of an amp. It's running normally, which I believe it is. Okay, time to look at the schematic. I need to look at it right side up. Well, this is a beautifully drawn schematic following lots of drafting principles here. First drafting principle is use the white space. See, there's no big areas of white open area here. They've constructed the schematic to utilize as much of the paper as possible. And look at this. Plate antenna. So yesterday I held up the back of the radio and noticed the tin foil on the back of it with a wire riveted to it. And I pondered, could this possibly be an antenna? And I think I concluded, no, they wouldn't make an antenna that way. Well, yes, they did. Plate antenna. Yeah, okay. I think you need more than just this plate, but let's just follow in from the antenna. So the antenna is a ground terminal. Notice the ground terminal goes through a capacitor. This is a very important thing to note. The ground terminal is not tied directly to the B- bus. Instead, it is tied through a capacitor. That's very, very important. If this capacitor is bad, if this capacitor is leaking badly, then the ground connection that's protruding from the back of the radio could be more or less thought of as the B-. If we follow the B- long enough and hard enough, we can find that the B- goes right to the plug. This is the essential problem with these radios. Now, like I said, in this radio, the chassis is isolated away from this B-, but in other radios, simpler radios, cheaper little 5-tube radios, often the chassis is connected directly to B-. You know, they save a little bit of wire that way. Save some wire, drive the cost down a little bit. But man, that raises the danger of that radio way up from one like this. There's the capacitor. that this would be a chassis indication here, and they're showing a small capacitor, 0.01 capacitor, connecting the B minus to the chassis, and this is the one that would drain out signals, if you like, or other things that could be, what other things could be in the chassis, you know, bugaboos, wild animals, anything like that, drained out into the B minus. Or another way of looking at this, we're bonding the chassis to the B minus so there can be no potential difference, at least no AC potential difference. This is sized in such a way that if you grab onto the chassis and then grab onto a water pipe, and this is plugged in such a way that this is the hot side, which is something we'll talk about in a minute, then you could be hanging on to 120 volts with your hand on a faucet. I would not recommend doing that ever. I wear rubber shoes, rubber slippers when I'm here, rubber-soled slippers, and I'm standing on a rubberized mat. That is on top of a ceramic floor, which is on top of a cement floor. So I'm feeling awfully safe in terms of grounding through my feet, but I do have hands and they do go places. There is no water pipe in my shop here, but all of my equipment on my bench is grounded back to the power system ground, which isn't even shown here at all. This is old enough that the North American electric system didn't involve, well, they didn't care about using polarized plugs. Instead, they counted on the manufacturers of devices like this to manufacture them in such a way that it became unimportant how you plugged, this way or that way, how you plug things in the outlet. But today, of course, the plugs are polarized, and you don't have any choice of how you get it in the outlet. And I might as well continue with this little discussion. So I've put temporarily a unpolarized plug on the radio, just as there was when I got it, and it's not a concern of mine while it's on my bench here and have it plugged into an isolation transformer. Before this radio goes home, it will get a polarized plug attached to it, and I will do my best to make sure that the hot side is here going to the switch and the grounded side is going this way, and that'll raise the safety of this radio quite a bit. I guess I can put it that way. Considering it's got a phono out the back, these are important things to think about and to understand, because different radios do things differently. You got to know what you got in front of you. Let's go find that phono plug. Here it is. Now, we got to look very closely at what they're doing here. So here's the phono plug. Yeah, let's look closely. Here's the phono plug. Let's follow the hot wire, the one inside, the signal wire. I shouldn't call it hot. The signal wire comes up through a shielded wire, connects into this switch arrangement. Probably this is shown in phono mode. This is probably the feed from the radio. And the answer would be, yeah, I think it is. Yeah, it's the feed from the radio. Yeah, because the output from this transformer is going to these diodes. So this is the audio feed from the radio coming through here. Capacitor to block any DC voltage that's developed up here. But you see, it's not connected to anything because the radio in this diagram is shown in phono mode. So the connection is from here over to here. Where's that? Actually, it's from here through here. Okay, so we'll keep following just the signal path. Another shielded wire. Interestingly enough, there's a wire. They drew this a little too close to these numbers for my liking, but the shield here is connected through this wire to the shield here, and it's just showing stopping. Let's follow the shield here. Now the shield's showing going this way, reaches a capacitor. On the other side, reaches B minus. So the shield is not hooked up to B minus except through this capacitor this way. What's going on over here? Very quiet, Jim. I don't know what they're doing here. What are they doing here? It's unclear to me at this point what this is doing. What is this? Is it a broken stick? They have a broken stick in the back of the radio? Well, I don't quite get it. So this is section 1. Here is section 2 over here. What they've done is they've taken a rotating switch and laid it out flat on the diagram here. This arrow is indicating the similar direction of rotation, or on the diagram, sliding. And this is a complicated switch. It's busy selecting coils and other stuff we'll get into in a bit. This one is just turning on and off the phono. What is the purpose of pin 7? Why did they put a dash here on pin 8? All good questions I can't answer at this point, but maybe it'll come clear as we carry on. So going back to the shield now, when you plug something into the phono input, the one wire is this one, the center wire, right, which we know is just going to the top of the volume control. And this is the slider part of the volume control. I guess this means more volume. It would, yeah. See, the volume control has a tap on the back. This is either for feedback, tone control, and loudness effects, something of that sort. Maybe not feedback. Yeah, here's the tone control right here. Engineers love this part of the radio. They do lots of interesting things with capacitors and resistors to affect the quality of the sound. We won't get into exactly what's going on here, at least not now. Just to go back. So basically, the signal coming out of whatever it is you've plugged in here, could be an iPhone, just fed into the top of the volume control. Where is there a capacitor? So there's a capacitor this way. That's the out audio going. The grid here will, the grid on the tube will build up a bit of a bias voltage on its own. That's limited, if you like, by this 10 meg, so it doesn't just build up, it's constantly bleeding downwards. And the capacitor here stops that small DC bias, self-biasing voltage from making it back to the volume control, making it back out to your iPhone, provided this capacitor is good and not leaking. It's a 0.01, so it's going to be one of those paper guys. Small voltage involved. If we follow this the other way, what's going on down here, the bottom is connected to B minus. Now this is usually a fairly large, 1 megohm. This is a large resistor here. So yes, this is connected to B minus, but through a huge resistor. So no real concern there about what happens if you have an unpolarized plug and you plug it in backwards, and this is 120 volts coming up here. 120 volts. Yeah, easily be 120 volts to natural ground, to earth, on anything connected to this B minus wire and the B minus wire itself. Isn't that scary? Why don't we try to find that capacitor frame at this point? There is, so here's the capacitor here. Showing it, often on these diagrams they have the capacitors, two sets of plates separated. On this one they've got them close together. One side is involved with what I imagine at this point to be these coils, which are the antenna coils, and the other one is involved with these coils, which are the oscillator coils. dotted line shows that they're mechanically interconnected. You turn one, you turn both. Now, what's the frame and what is not the frame? Well, we're going to take now, in these capacitors, the rotating, this is the part that's a little hard to believe, the rotating part of the capacitor, the plates that move, are tied to ground, are tied, well, in this case, would be tied to B minus. Can we find how this might be tied? There it is. It's tied through a capacitor here. Okay, that's just a bit surprising to me. Many connections going in here. Goodness knows I have to spend a lot of time figuring out the switch. So does this wire, this B minus, does it make any solid connections in? So that one's capacitorized, this one's capacitorized, not this one. Bottom of this coil. More switches to figure out at some point, maybe. Up here, bottom of this coil, over here. Would look like this piece. It's in phono mode right now, so this piece is actually farther away than it normally would be when the radio is operating. So we move this one snap forward, this piece hits here, and this piece catches this one. So we've now hooked up this through the coil, through the switch, to here, come all the way up here, all the way up to the cathode. So this is a part of radio design that I don't fully understand how they do this. The cathode will be essentially directly connected to the B minus. Yeah, I don't think I'm going to analyze it any further than that at this point. I'm going to leave it just hanging like that. Wait a minute, maybe, yeah, a little complicated to sit here and do this live. This could take quite a while to sort everything out, making mistakes left and right. So what have we discovered? Let's just recap. Phono input. The outside of it is connected to B minus through a small capacitor, a 0.03 capacitor. Not connected directly to B minus, of course. This capacitor is critical in maintaining this safely. You'll also find that the hot lead is connected to B minus, but through a huge resistor. Not really. When I say hot lead, I shouldn't say hot. I should say signal lead. Not a big deal. And the radio is disconnected when phono is connected. There are radios out there that when you flip it to phono, the radio remains connected. And if you tune in a station, you'd be listening to the station and the record player at the same time. Better radios obviously do this kind of thing, but not all radios. Okay, let's follow the signal right through the radio now. Go back to the antenna. The antenna is connected to this coil, and we'd have to analyze these switches quite a bit to sort it all out. Looks like there's a cascade of coils. This one, this one, this one, but these switches are manipulating things here. In some radios you're selecting only this coil, only this, and then only this. In others you're selecting this, then you're selecting this, then you're selecting all of this. Different radios do things differently. Probably all basically in an effort to get the best performance with the cheapest cost is really what they're after, of course. So the antenna signal right at the bottom here is capacitorized to the B minus. So you can imagine the antenna signal is basically between the plate and the B minus going through these coils. Coming out of the other side, these transformers is really what I should call them. You see each one of them has a tuning adjustment to tune them up to, now this would be like a low Q arrangement, so you tune this once, kind of center of the band, sort of, not maybe really, but you tune it once and then this is good for the entire band involved. tuning is part of the alignment procedure. And now the output, where's this side going? So this side goes to this side of these capacitors. Other side goes to the other side of this one capacitor. Ooh, no, this is going to be the oscillator capacitor, doesn't it? Yeah, I'd have to analyze the switches again to sort all that, but this has to be the signal side here because of where it's going, onwards and upwards onto this grid of the 12BE6. Now, it's not the only signal in this tube. So the antenna signal is here on this grid in this tube. If we follow this grid, grid 1, we'll find out there it goes down towards all these coils, which are the local oscillator coils. So when you tune the radio, when you turn the dial, you're tuning against these coils with the antenna system and these coils with the local oscillator. For an oscillator to work, it must get some feedback from an amplification device. So some output from this tube has to get back into here. Now let's just see if we can figure out how that's done. How is that done? How are you getting back there? So sometimes the cathode current is run through the coil. So follow the cathode back. See, it's getting involved here. So when this guy slides over and this part touches here, you're connected here, the first case, and there. So the cathode circuit from B minus runs through this coil. So all this tube current is going through this coil. So that's the feedback because it's fed back through transformer action into this side of the coil, and it's on its way to grid number 1. So that's how it's done. This is very typical of a lot of radios. Use the cathode current to generate the feedback necessary to set up the oscillations. The oscillations are controlled by capacitors. You see the trimmers here, and there's another one down here. Oh, another one over here. This is probably for AM radio here. We could take a wild guess and say probably this one is also AM, because you'd think the draftsmen and engineers would arrange this diagram to be as least confusing as possible. Not necessarily the case, though. Is there something different about this coil from these others? Well, it has this capacitor sitting here. These guys don't have a capacitor. It's probably the case. This is probably the AM coil. We can find out, but I won't bother right now because we don't need to know. Sometimes you just need to know something exists. You don't really need to know how it works in detail. So we see there are 2 screens in here, 2 screen grids. So the first screen grid is blinding this grid to not only the plate but also this grid too. So it's not influenced to any great degree by what's happening with these other grids. This screen is trying to block the view of this grid so it cannot see this plate. And so what that does essentially is it reduces the interelectrode capacitance. For these tubes to operate at higher and higher frequencies, or when these tubes operate at higher and higher frequencies, the interelectrode capacitance begins to affect them. This is why you can't use a triode in high frequency applications, because the grid is capacitively coupled to the plate. And once you get the plate really going, some of that really going gets back on the grid. Well, then you've got an oscillator set up, and that's what it'll do. It'll oscillate. So you put in these screen grids, which it was discovered that you just put a voltage on these grids, basically a steady DC voltage, similar to the plate voltage, and these guys become decoupled, if you like, from the plate. They can't see it. I said, well, wait a minute. If you put these grids in and run them at the voltage of the plate, don't they become plates? They do. They become crappy plates. So a sacrifice is being made. Some of the electrons are going to find their way onto the screen and head out this way. And that's why there's a screen current on these things. Sometimes it can be substantial enough you got to be careful about it. Follow this along. It eventually encounters this resistor. I won't go into that. That's all along. I don't talk about that resistor. Let's go back here. So again, I don't know everything. And thank God I don't, because that means it's fun. There's stuff for me to learn. If I knew everything, this would be a bore, wouldn't it? So here we see plate voltage listed here. Plate voltage again. Plate voltage here. Not very high, 115 volts. Can't be very high. There's no power transformer to transform out a high voltage. It's got to work with what's available in the outlet, which is 120 volts. You could get a little more voltage here, and some of these radios might be up around 130 volts at this point. Something like that. This one's not quite that high. 100 volts. So what's going on in this tube now is the two signals are being mixed in this single electron flow being influenced by this grid and this grid. And the consequence of that is when you mix two things together like that, and you might require a non-linear operation of the tube. I'm not sure of that. The result is you get, oddly enough, you get the two initial signals coming out of the tube, the antenna signal and the local oscillator signal, and you get a mixture of them, the sum and the difference. So if you add them together, let's just play around here. Let's assume that we're tuned to around 500 here, and the local oscillator is running about a million hertz. Out of this tube is going to come 500, 1 million, plus the two added together, 1500 kilocycles, and the difference. Now the difference is real interesting. The difference in this case would be 500, a million, would be 500. So you'd have, oh, that's a bit of a problem, isn't it? You'd have two of the same frequency here. So obviously they don't use those numbers that I just used, because you'd have the 500 here and the 500 difference. That doesn't sound so good. So if I pick different numbers, we would have 4 different frequencies coming out. In reality, there's 4 different frequencies coming out. So on here are 4 different frequencies coming out. And they face this tuned transformer. The tuned transformer is tuned for one of those 4 frequencies. In this radio, I believe it's 455 kilohertz. So if on this wire there is a 455 kilohertz signal, it will transform through here and show up on the next tube. Everything else, not going through here. Not going through. So in a sense, the other 3 signals are discarded at this point by the radio, rejected, grounded out, killed, whatever word you want to apply to it. But if there's a 455 here, it will go through. So if we use a real example, let's say we tune the radio to 600 kilohertz, and we want the 455 to come out at that point. So if 600 here, we would need, on the local oscillator, a difference frequency of 455. So if we add 455 to 600, we get 1,055 or 1,000,055. So if we tune this oscillator to 1,000,055, the two of them will combine, the 600 and the 1,000,055, to give you a 455. If I got the number slightly wrong, it doesn't matter. I'm just trying to make a point. That's how these radios work. What's the advantage of that? Well, it's a lot easier to build a radio that's designed to tune one frequency all the time than to build a radio that's designed to sweep through a range. The front end is sweeping through a range, but after that, through this conversion technique on a local oscillator, all the radio needs to receive is 455 kilohertz. So these things can all be tuned to 455 and just left there, waiting for a difference frequency to show up that matches what they're tuned to. Okay, 455. So things get a little simple through this next part. So the 455 that's been produced by the mixing in this tube goes on its merry way through here, gets on the grid, gets amplified by this tube. This is a critical, this is the important tube in the radio for making it very sensitive in that. The output, stronger now, comes into this coil. Same thing happens. 455 makes it through. If there was any junk that came along out of here somehow, it's just going to have a harder time carrying on because they have another tuned circuit here only for 455. So conceivably, by the time you get here, it's just a lonely 455 kilohertz signal, modulated, of course, by the program material. So the output here is rectified by these two diodes. In this case, they're using both of them. Different radios do different things at this point. This one, they just tied them together. So you have both plates working. So this rectified signal now, it's a half-wave rectification, is sent down through some filtering with capacitors and blocking with capacitors to destroy, if you like, or block the RF that's coming out of here and leave only the audio, which will now be recoverable because of this diode operation here. Recoverable or will be there. The audio is sent to the volume control. So the audio comes down through here, through this capacitor. More and more the RF is being blocked or negated in various ways. Often there's a small capacitor up here that goes to the would go to the B minus. I don't see one in this radio. Through the capacitor, any DC that's up here, which I'll talk about in a moment, won't make it through here, and of course when you're in radio mode, these two things are tied together, and voila, the audio hits the top of the volume control and what happened? Whoop. Carries on. Wasn't that? It woke everybody up. Okay. Now, coming out of here, not only is the audio, but because you're using a rectifier on an AC signal, you get a DC component just being filtered and fooled around with here to try to smooth it out into straight DC. And that goes to B minus. So here it is. This is the capacitor I mentioned. Capacitor basically taking the RF to the B minus and killing it, more or less. This is a filter, I guess, to help with this. So down here we've got some DC coming. The stronger the output here, the more DC. They've arranged this in such a way that this DC is actually negative relative to this B minus. That's very important. You could do this differently. Flip these wires around you to get a positive voltage here. That's not useful. The negative voltage is useful. What do you do with it? You send it off to some grids. Now, grid circuits are typically very high impedance, and so you don't want to destroy that, so you put a big resistor here. Because there's really nowhere for current to flow through here, because it ends up dead ending in a grid, in the tube, there's no complete circuit. The current flow through this resistor is, well, not really there. It's not really there. So you don't really get a voltage drop across it. So if you got a couple volts here, negative, you get a couple volts here, negative. And that voltage is sent, as I already showed you, through the coil. Tricky, eh? To get access to the grid, and likewise, that same DC voltage works its way down here through another big resistor and onto the signal grid. Now, these tubes are designed so if you manipulate the bias voltage on these grids, the gain of the tube changes. So that means if, in this case, if you put a higher and higher negative voltage on the grid, the tube's gain goes down and down. So what that means is, the stronger the signal here, the higher the grid potential, the more throttling that takes place at the front of the radio to reduce the output here. That's an automatic volume control, like a governor type arrangement. And all this stuff is arranged so that everything works just the way you'd like it to work. And this means, ultimately, as you tune across the radio bands, every station you tune in delivers a similar volume out of the speaker. The local stations don't blast out of the speaker, and the distance stations aren't inaudible. But what it also means is when you tune between stations and there's no signal coming out of here, you get no DC voltage bias or minimal bias back here. And these tubes are just amplifying for all they're worth. And what do you get? You hear the noise on the antenna. So when you tune in a station, you're listening to a guy talk, it's all very pleasant. You tune off and you hear pshh, and you think, well, that's what must be out there in radio land between stations. No. What's happened is your radio has turned itself up a lot, and that's why you're hearing the hiss. It's a real annoyance if you're a serious radio listener, like a shortwave listener. The automatic volume control systems cause the radio to produce a lot of noise between stations. It goes away when you tune something in, because the voltage develops again and the DC shows up on the grid and the gain goes down, and voila. So it's much more pleasant in a bigger, better radio to turn off the automatic volume control, take manual control over the RF gain, so you control this voltage on the grids directly with a little knob. And as you tune between, say, short wave stations, the noise doesn't come roaring out of the speaker. It, in fact, gives you a much better idea of what is really going on in the universe, as opposed to the trick being played by these tubes in a radio like this one. Okay, moving on. So we've managed to get the audio available basically by chopping half of the signal away with these diodes. The other half you can manage to recover the audio. Sometimes they call it the audio envelope. I don't really quite like that word, but it's kind of what it's like. The audio goes into the top of the volume control. If you slide this guy up here, you get loud volume. Slide him down there, you get no volume. Some portion of the signal voltage, the audio voltage dropping on this big resistor, is taken off. Again, very little or no current flowing up here, and there's a 10 meg resistor here. So the audio gets through this capacitor. It leaves the DC behind that may have gotten all the way through this, and voila. Now, how's this guy biased? So this is a two-part tube. One part are these diodes, the other part is this triode. They have really nothing to do with each other except they share a glass envelope. So don't think they're all working together, they're not. So the signal is sitting on the grid here, but the grid would be biased at 0 volts. See, it's tied to this negative. So what would happen is, much of the time, the grid would appear positive relative to the cathode as the signal swings up and down. The cathode is tied right to B minus. So when the grid goes positive, it becomes a little plate and it absorbs electrons, and it'll pick up a negative voltage. That negative voltage would dissipate quickly, except it can't go through the capacitor, and it's got a 10 meg ohm resistor here. So the electrons pile up on the grid, and the grid becomes a little bit negative. How negative? Negative enough that the most positive pulse or positive voltage on the grid is equal to the grid bias. It generates the grid bias. It's called self-biasing. So that's really critical. If this isn't working, if somehow, I don't know how this, well, one way, if this were to open. If this went open, they'd be relying on, well, I wouldn't even say that. If this goes open, then this grid voltage is probably going to climb 2 negatives. It's probably going to go 2 negative, keep going more and more negative over time. and you can't have that. So to bleed off some of the charge, big resistor stuck here, just a few electrons skittering through here. Of course, in reality, electrons hardly move in any of these circuits. Electrons are hardly covering any distance in these circuits, in any circuit. They don't fly around at the speed of light, nothing like that's happening whatsoever. So anyway, not to dwell on that. So now we have the audio signal sitting here. This tube generates a nice voltage swing to be applied to the grid of the output tube, which is designed to produce a fair bit of power, and part of that is having a fairly large voltage swing on the grid. The grid voltage here is created in a different way rather than voltage up the grid with a bias voltage of some sort. The cathode is pushed positive by this resistor, 150 ohm resistor here. These are usually bypassed. Here's the bypass down here. This is the 3-part capacitor. 2 parts related to the power supply, I'm pretty sure. 1 part just here to do the bypass. So the signal can find its way to ground through this fairly large resistor. There it is, connected there. So this is called the cathode resistor. It's very important. They've written the voltage you should measure right there, 6.2 volts. That's essentially the grid bias. Except instead of changing the grid voltage, they've changed the cathode voltage. Very, very typical technique used for supplying, for arranging the bias in these kinds of tubes. Okay, so here we've got the screen, and then this is a beam power tube, and they're trying to indicate that by showing these structures in here. Beam power tube has characteristics which I'd have to read up on it again, but it has certain characteristics which are very beneficial in a power tube. So the audio output now being strengthened a lot here. It's fed down through this transformer and onto B minus. The audio is transformed out to the speaker. So the speaker impedance is low, 8 ohms in that range, 4, 8, 16, we don't really know, something like that. And the transformer is basically an impedance matching device. So, because this tube is looking for a fair bit of impedance in the plate. If you want to get maximum power transfer, you have to do things just right here. So there's the tube has to sense a impedance here that's sufficient for its purposes. Leave it at that. Now, what is this guy doing here? What is he doing here? I may not have an answer for this. I don't think I have an answer for it. I'm not going to be able to explain exactly what's going on. If you notice the 2 sections of the capacitor here, one section is hooked up on this side of this resistor, this is part of the power supply, this resistor, right onto the roughly rectified power coming in. Look, this isn't even a full wave rectifier, it's just a half wave rectifier. And the power on this side of it, oh look, I see what's going on. It's going up over there and then getting into here. Yeah, exactly how this works I don't know, but it would look to me like this is how the power gets up to the plate, and some of it comes back this way through this resistor. It's too bad they drew this like this. Fooled me. Fooled my eye here. So we have a little bit of an inductor involved here. Don't know exactly if that's part of the filtering. Maybe it is. Come through this 1500 and find another big capacitor sitting here. So heavily filtering this. The point is, this side not filtered as much as this side. This is much more highly filtered power, so it's more pure DC. Is fed to the plates. of these earlier tubes. Goes through this coil. Whoops. And right here, goes through this coil. Come on, computer. Goes through this coil. Gets to the plate. Using better filtered DC on these early tubes, because a little bit of humming ripple is going to be magnified by these tubes, by this part of the circuitry, and you're going to hear a hum come out the speaker. But if you send not so well filtered audio, or DC rather, up to the output tube, it won't matter because you can't hear it. It's there, but it's so low, it's inconsequential. That's just a little bit of a money-saving deal. Why over-filter things when you don't need to? Save some money, make your radio cheaper. Where did my cursor just go? My cursor. There it is. Now, let's look at the power supply. Maybe I should have started there, but I'm ending there. So, power supply, very simple half-wave rectifier. There's no cathode in here. The heater is the cathode. And we see that all the tube heaters are in series. And we need to ask, what's that? Well, that must be the light. I mean, it looks like a light bulb symbol, doesn't it? And it's just hooked right across the power. So that's a 120 volt light bulb that's in the front of this radio. It would appear, am I seeing things? So all the tubes are in series, yeah. Just right across the line, right across the high voltage, or the 120 volt line. I think it's just the way they've drawn it. I'm thinking some current is flowing through this bulb here, more than just the current that powers the bulb. I think I'm seeing things. I mean, if you took this wire and just stuck it over here, I wouldn't think such silly things. Okay. So we have a 33 ohm 1 watt resistor here. This could be a current limiting resistor. I'm not sure why it's in the circuit here. And we have a small capacitor tying back the B plus to the B minus. So it's possible what this capacitor is doing is it's draining out any RF that is managed to arrive at the power supply from up here in the rest of the radio circuitry. Because you cannot rely on these electrolytic capacitors to pass high frequencies. They don't do a good job of it. They're certainly okay at 60 hertz, but at a million hertz, they're not so good. So that could be what this guy is for, like a safety valve, just in case some RF is getting all the way here. And they draw it over here for convenience sake. They could have probably drawn it somewhere else. Yeah, I'm not sure. And again, I could be wrong about these kinds of things. I think I'm probably 90% right on the stuff I'm saying, and 10%, maybe not. Your challenge is to figure out which is the 10%. So a few notes here worth looking at. Arrows on potentiometers and switches indicate clockwise rotation of shaft. All switch sections are shown in the extreme counterclockwise position of the switch. Switch 1 is in the phonograph position. All DC voltage is measured to B plus with a 20,000 ohms per volt meter. That's a very good voltmeter. That means these measurements are probably absolutely correct. They have not been adjusted or written down to match a bad voltmeter. That's a pretty good voltmeter. Now I'm going to be using a vacuum tube voltmeter. It's at least this good, probably better. Test voltage, got to be 117 volts. And information about the coils can be helpful. Hopefully we don't need to look at that and study it, because we're studying these things carefully, that means there's something seriously wrong with the radio, and I don't think that's the case. So no need to dwell on them, but they're here. See, it's good to know they're here. Switch numbering system. Anything funny going on here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nope, they're numbered in order. Viewed from front of chassis. So you can relate these numbers to this switch. And of course this is showing them physically, positionally also. You can recognize it when you look at it, if you need to. Okay, so I've developed one heck of a crick in my neck here, standing here doing this. We're not going to study this till we need to. This is the, again, this is the alignment information. I think that's it. I really talk about draining things out. I've drained my brain out on this, so let's just see how much time I've used here. Well, as it turns out, I've spent an hour talking about the radio without actually doing anything to it. I did want to spend quite a bit of time there. The owner of this radio is interested in this kind of stuff, and I think he will appreciate a detailed description of the schematics, so that's why I spent so much time on it. I don't think we're going to get any work done on this today. I'm going to stop and remove the crick from my neck, which is just killing me here. I'm hunched over. Oh my gosh. Okay, so I managed to get the crick out of my neck. Let's just spend the last part of this video just trying to identify some of the key capacitors that are related to the chassis connections and stuff like that. So the first one is this one. So there you can see the connection to the chassis there, and the other side of it connects to what I'm sure is the A B minus point. The B minus is winding its way all through this radio on different wires, mostly black. So connection points to B minus can be anywhere in here. So another interesting one is the ground of the antenna. This is the antenna live part, and you can see it's coming in and going to a coil, probably a transformer really. And the other side, the ground, is not grounding right to the chassis. Instead it's going through this capacitor and then tying again to what I imagine to be, well, it's the same terminal as this guy. So this is almost certainly B minus. There's a black wire going over here, pile of stuff connected. It's going to this. This is typically a ground point, not always, but so yeah, B minus. So we have two B minus isolation capacitors, I guess we can call them. This maybe a safety capacitor, you can call it that. Now if we look at the phono input, which is here, they're coming on a shielded cable. This is a shielded cable here, shielded and covered with insulation. I can see the shield is connected by a wire to this point. You can also see that this connector is actually insulated from the chassis. You see these big rivets here. It looked like, oh, this outside part of this phono plug must be grounded. No, it's not. That's a non-conductive material. So there's no grounding to the chassis here. So we follow the wire around. It comes over to this location. I can see the center conductor is connected to a terminal on the switch. The shield is connected to this black wire over to this side where it encounters a capacitor. Not sure where that's going. That's going to a ground point also. So here's another grounding capacitor. I don't remember. 0.027, I think I do remember this one. And that black wire is also connecting to the shield of this shielded wire, which is then traveling further along, gets to here. The center conductors produced here and connected to the must be top of the volume control, and the shield is just left. It's just dead-ended here. It doesn't connect to anything. So I think we could say there's 3 column safety capacitors in here 1, 2, and 3. That if these capacitors are leaky, then there is some danger of getting a shock or damaging something you might be plugging into the phono or into the antenna, or who knows what you're doing with this radio. So now, what about the shock hazard that I exposed myself to years ago with one of these kind of radios, where I contacted the frame of the capacitor and the chassis at the same time. Now, it was a long time ago this happened. I didn't fully understand how I got a shock at the time. I was quite stunned, in fact. Shocked and stunned. But now I think probably what I did, at the time I may not have been using an isolation transformer. So that would mean I'm plugging it basically into the wall, and depending upon which way the non-polarized plug is put in, the chassis could be live. It was a smaller, cheaper radio. I think if I pulled out the schematic for that radio, which I can't, and I'm not about to, and I studied it long enough, I discovered that one side of the power line was connected to the chassis and the other side was connected to the frame here. And then I just touched both. And another possibility is the chassis was in fact handled just like this radio, basically an isolated chassis, not connected directly to B-, but only through a capacitor. But I may have placed the ground from one of my pieces of equipment, on this test equipment, onto the chassis. I don't know, I can't remember, it was a long time ago. I certainly remember the shock. And I've been wary ever since. So unfortunately, some lessons are learned the hard way. You do not want to get a 120 volt shock or any shock. They are all dangerous. It's the only way to look at them. There's never a time you get any kind of shock that you should giggle about it, because under slightly different circumstances you might not be around anymore. Okay, I think that's the end of what I can do today. Tomorrow, I think the first thing we'll do is we'll get rid of these three capacitors that I've identified. We'll test them out, see how they stack up. Like I said before, they look really good. Maybe there's no concern in this radio with them. But there's really only one way to find out. That's to remove one and test it. And it's time for them all to go anyway, I think. So thanks so much for watching this video. Sorry I'm not actually doing any work on the radio. That'll come tomorrow. See ya.